So a group is a set with closed, associative, binary operation. That means it takes two elements of the set, this binary operation does, and returns another element of the set. And when you have two of these operations done in a row, it doesn't matter what order they're done. A group also has to have an identity and inverses. Now, a set with a closed binary operation is called a magma. It's just a set with a closed binary operation. When you add associativity, you get what's called a semigroup. When you add inverses, you get a quasi-group. When you add to either of those an identity, we'll call it E, get a loop from a quasi-group. You get a monoid from a semigroup. And then if you add to either one what they're lacking to be a group, you get a group. There. I want to show you some examples of groups. One example is a symmetric group. A symmetric group is the set of a set of permutations. So for instance, a symmetric group of three elements is the set of permutations of three elements. Now, how can we call this a group? To be a group, we need a binary operation. We need some way of putting these two permutations together. Well, the way to do that is first do one and then the other. All right, so for instance, we can, well, first let's give these some more descriptive names. And these names will indicate the sort of thing they do to the, let's call this one the original. All right, so the original does nothing, does not change the original. This, you can see that from the original, the second and third elements are switched. So I'm going to write that like this. The second element goes to the third goes to the second. The first two elements are swapped. In this permutation, the first element is sent to the third slot, so the first element is sent to the third slot. The third element is sent to the second slot, and the second element is sent to the first slot. All right. And the operation is the composition of permutations. For instance, let's compose these two permutations. And we read from right to left. Let's start with 1 this permutation, this swapping, does nothing to 1, so 1 goes to 2. This swap sends 2 to 3, and then 3 is not sent anywhere, so 2 gets sent to 3. 3 gets sent to 2, 2 gets sent to 1, 3 gets sent back to 1. So the composition of these two permutations, doing this one and then this one, is the same as doing this permutation. So that composition is our operation. Here's our identity, and I'll leave you to check that it's associative. Inverses, it's hard. Well, it's easy to see with these three elements. They're their own inverses. It's harder to see, but these two elements are inverses of each other. At any rate, we can generate GER subgroups. Take a subset of the set on which the group is defined and apply the binary operation in all possible ways. So for instance, we can take this element and generate the subgroup. Find the subgroup generated by that element. Well, that element itself is in our subgroup. If we compose it with itself, we get the identity back, and that's it. We can multiply these two with each other and with themselves all day long, and we never get outside this set. So this is the subgroup of S3 generated by this permutation 1, 2. Let's look at another example. The subgroup generated by this cyclic permutation. These permutations are all cyclic in the parentheses there. Not all permutations are cyclic, but the ones written in a single set of parentheses are. Okay, if I take 1, 2, 3 and I compose it with 1, 2, 3, 1 gets sent to 2, 2 gets sent to 3. 3 gets sent to 1, 1 gets sent to 2. 2 gets sent to 3, 3 gets sent to 1. Okay, that's fine. So if we multiply this 1, 2, 3 with itself, we get 1, 3, 2. That's another element. If we multiply 1, 3, 2 by itself, we get 1, 2, 3. If we multiply 1, 2, 3 and 1, 3, 2, 1 gets sent to 3, 3 gets sent back to 1. 2 gets sent to 1, 1 gets sent back to 2. 3 gets sent to 2, 2 gets sent right back to 3. So the product of these two is the identity. And this is the subgroup generated by 1, 2, 3. It's also the same as the subgroup that would be generated by 1, 3, 2. Okay? So that's one class of groups, symmetric groups. Another class of groups are the dihedral groups. All right, dihedral meaning two faces. They're written with a D and a 2N. I'll explain why a 2N here in just a bit. The set is the positions of a regular polygon considering front and back. In other words, a subset of the permutations on n labels where the cyclic adjacency is preserved. If A is next to B, A is always next to B. No permutation takes A away from B. That's what I mean by the cyclic adjacency. And if, say, D is on the end of a list and A is at the beginning of the list, A and D are considered to be next together. Let me show you how that works. Take a pentagon, for example, and label the corners. All right. So we could call this the original, or sorry, no, not that permutation. We call this the original permutation, and here 1, 2. All right. Well, what sort of permutation would that be? 1 gets sent to the second slot, 1 gets sent to 2. 2 gets sent to the first slot, 2 gets sent to 1. Okay. What about 3? 3 gets sent to the fifth slot, and the fifth gets sent to the third. All right, so this is a permutation on 5 labels that actually preserves the cyclic adjacency. Or you can think of it as just a polygon, a regular polygon being turned around, picked up, flipped over, and put on to itself some way. Okay, here's a question for you. How many elements in this dihedral group? Pause the video, try to work it out, and come back. All right, here's the answer. If we are generating a list of these n labels that has the cyclic adjacency preserved, we have n labels to choose in our starting position. We can choose any of those labels to be in some starting position. But then it has 2 labels next to it, and so we have 2 choices of what to put, say, to the right of that initial label, and then everything else is forced. So 2n is the number of elements in D to n, and that's why it's called that. Let me give you an example. D8. Okay. 8 is 2n, n is 4. This is the positions of a regular polygon with 4 sides, a square. So here's a square. 1, 2, 3, 4. Here's another square. 1, 2, 3, 4. So we're trying to write down, I'm trying to write down all the elements of this dihedral group, and we know there's 8 of them. All right, what are the rest? Well, choose the 2 to be over here instead of over there. 1, 2, and then 3, 4. Those are forced. And then 1, 2, 3, 4. 1, 3, and 1. There. Oops, that one got kind of messed up. We can call this the original. And what physically do we do, or well, geometrically do we do to get from here to here? It's a rotation. A rotation there. And that's why this element is called r. This we do 2 rotations to get from here to here, so this is called r squared, r cubed. Here we flip from one side to another, s. Flip and then a rotate, so a flip and then a rotate. A flip and then 2 rotations, a flip and then 3 rotations. Again, let's look at a subgroup. Let's say the subgroup generated by flipping and rotating twice. Oops. All right, if we flip twice, we get back to the identity. Very nice. Definitely, if flipping is one of our generators, flipping is in the subgroup generated. If rotating twice is one of our generators, rotating twice is, well, okay. And then we can multiply these two to get this r squared s. And that's it. If we multiply these two, we get that. If we multiply these two the other way, we get that. Notice that this group is not commutative. R and then s is not equal to s and then r. S and then r is this, but if we rotate and then flip, we get this thing here. Okay. At any rate. But check this, that r squared s is equal to sr squared. And that sr squared times itself is the identity. R squared times itself is the identity. Any two of these two multiply to give that, these two multiply to give that. So we're done. This is the subgroup generated by s and r squared. It's half, and this is actually isomorphic to dihedral group 4 to 4.